A solar panel can power a house for 25 years, yet it starts as ordinary beach sand. That sand is melted at over 1,400 degrees, but comes out purer than almost anything else manufactured on Earth. A wafer thinner than a human hair somehow survives a machine that slices it like deli meat without shattering. And a panel sealed for outdoor life in the desert, the Arctic, and everywhere between is expected to never be opened again. That shouldn't be possible. So how do factories turn raw sand into a device that silently converts sunlight into electricity, reliably for a quarter century at massive global scale? Let's step inside and find out. Silicon is the second most common element in Earth's crust. It's in the sand under your feet. But the silicon in a solar cell isn't just clean. It has to be 99.9999% pure. Get that number wrong by even a fraction, and the whole cell fails before it's even built. It begins with quartz, a silicon-rich sand mined from quarries around the world. Trucks deliver it to a furnace facility where it's dumped alongside carbon in massive batches. On screen, the raw quartz looks dull, gray, unremarkable, nothing like the sleek black panels it will become. Inside an electric arc furnace, the quartz and carbon are heated past 1,400 degrees Celsius. At that temperature, a chemical reaction strips away the oxygen, leaving behind raw metallurgical-grade silicon, around 98% pure. That sounds impressive, but for solar use, it's nowhere near good enough. The silicon is crushed, then reacted with hydrochloric acid to form a liquid compound, which is distilled and purified again and again in tall separation columns. Finally, the purified gas is exposed to superheated silicon rods inside a sealed reactor. Layer by layer, silicon atoms deposit onto the rod over several days, building it up like stalactite growth in reverse. When it's done, that rod is 99.9999% pure, what the industry calls 9-9's silicon. It's melted one final time and slowly pulled upward while rotating, forming a single cylindrical crystal called an ingot, sometimes over 6 feet tall. A single misaligned rotation speed during the ingot pull can introduce microscopic defects invisible to the eye. Defects that won't show up until the panel is already installed on someone's roof, quietly losing efficiency for years. Not every ingot is made the same way. This slow, rotating pull method produces what's called monocrystalline silicon, a single uniform crystal with no internal grain boundaries, which is why monocrystalline cells are the darker, more uniform black panels typically seen on residential rooftops. A cheaper alternative exists too: pouring molten silicon directly into a square mold and letting it cool. That method produces polycrystalline silicon, recognizable by its fractured, bluish, mosaic-like appearance. It's faster and less expensive to make, but the multiple crystal boundaries scatter electrons less efficiently, which is why polycrystalline panels typically convert slightly less sunlight into usable power. That flawless, glass-like silicon ingot is now ready for the next transformation, from a solid cylinder into something almost impossibly thin. That ingot is solid rock. In minutes, it's sliced into wafers thinner than paper. A single silicon ingot holds enough material for thousands of wafers. Each one will be sliced to a thickness of under 200 microns, about twice the width of a human hair, using a tool that has to cut without wasting a single unnecessary gram. The cylindrical ingot is first squared off into a block, trimming the rounded edges into a rectangular column. This shaping step alone can waste up to 10% of that painstakingly purified silicon, which is why factories recycle every shard back into the melting process. The squared ingot is mounted onto a wire saw, not a blade, but a single continuous wire, sometimes over 500 kilometers long, strung back and forth hundreds of times to form a cutting grid. Coated in an abrasive slurry, the wire moves at high speed while the ingot is slowly fed downward, slicing hundreds of wafers simultaneously in a single pass. Each wafer that emerges is cleaned, chemically etched to remove micro-damage from the cutting process, and then textured, its surface etched with microscopic pyramids invisible to the naked eye. Those pyramids aren't decorative. They're engineered to trap incoming light, bouncing photons downward instead of letting them reflect away, so almost nothing is wasted. A wafer this thin can crack from a temperature change as small as a few degrees during handling, which is why, in most factories, human hands never touch it. Robotic arms do the entire job. What started as a chunk of purified rock is now thousands of paper-thin, light-trapping wafers, ready to become active solar cells. A wafer alone can't generate power. It needs to be turned into a working cell. This is the step where silicon stops being a material and starts being a machine. Through a process most people have never heard of, a plain gray wafer becomes a device that generates real electricity the moment light touches it. Each textured wafer moves into a diffusion furnace, where it's exposed to phosphorus gas at extreme heat. This isn't decoration. It's the step that gives the wafer its electrical personality, creating the two-layer structure that every solar cell depends on. The phosphorus atoms bond into the top surface of the wafer, creating a negatively charged layer sitting on top of the naturally positive silicon beneath it. Where those two layers meet is called the p-n junction, and it's the single most important boundary in the entire panel. It's what allows sunlight to knock electrons loose and push them in one direction, creating usable electric current instead of random, useless motion. Next, a thin anti-reflective coating is applied, giving the cell its recognizable deep blue or black tint and further reducing wasted light. Finally, ultra-fine silver and aluminum paste is printed onto the surface in a precise grid pattern, forming the metal contacts that will carry electricity out of the cell. The cell is fired one last time at high heat, permanently bonding those contacts into place. That thin grid of silver lines has to be printed with a precision measured in microns. Too thick and it blocks incoming sunlight. Too thin and it can't carry the current. The cell can lose meaningful efficiency from a printing error smaller than a grain of salt. Before it ever leaves this stage, every cell is flashed with a burst of simulated sunlight and electronically sorted by its exact output. Cells that perform almost identically are grouped together and will end up in the same panel. Because pairing a strong cell with a weak one doesn't average out their performance. Instead, the weaker cell drags the entire string down to its level, the same way a slow runner sets the pace for an entire relay team. This sorting step, invisible to anyone looking at the finished product, is one of the reasons two panels that look identical can perform noticeably differently. A single wafer has now become a functioning solar cell, but on its own, it only produces a small trickle of power. One cell barely powers a calculator. Dozens of them, wired together, power a home. A finished solar panel will spend the next 25 years bolted to a roof, exposed to hail, snow, UV radiation, and temperature swings from freezing to scorching, with no maintenance, no replacement parts, and no room for error. Roughly 60 to 72 individual cells are laid out on an automated line and connected in rows using thin copper ribbons soldered directly onto those silver contact lines. This string of cells is what will eventually sit beneath the glass viewers recognize from rooftops everywhere. The connected cell strings are layered into a sandwich, tempered glass on top, a soft encapsulant film both above and below the cells, the wired cell matrix in the middle, and a weatherproof polymer backsheet on the bottom. This entire stack is fed into a lamination machine where it's heated and vacuum pressed at once, melting the encapsulant so it fuses every layer into a single, sealed unit with no air pockets and no gaps for moisture to creep in. From there, an aluminum frame is pressed around the edges for structural rigidity, and a junction box is attached to the back, housing the electrical connectors that will eventually link to an inverter. Before it ever ships, every single panel is tested under a machine that simulates full sunlight for a fraction of a second, measuring its exact power output and flagging any cell with a hidden defect. A single trapped air bubble during lamination, invisible from the outside, can create a hot spot that slowly degrades the panel from the inside over years, which is why that vacuum sealing step is one of the most tightly monitored in the entire factory. But testing doesn't stop at that single flash of simulated sunlight. Before a panel design is ever approved for mass production, Sample units are pushed through a gauntlet meant to compress 25 years of weather into a matter of weeks. Panels are baked at extreme heat, then flash frozen, cycled back and forth hundreds of times to check whether the glass, metal frame, and internal layers expand and contract at compatible rates. Others are blasted with simulated hailstones fired from an air cannon, soaked in humidity chambers to test whether moisture can creep past the seals, and mechanically loaded with the equivalent of heavy snow to confirm the frame won't buckle. Only after surviving that entire battery of abuse does a panel design earn certification to actually be manufactured at scale, which means every finished panel rolling off the line has already, in a sense, proven it can survive decades before a single one is ever installed. What began as sand is now a sealed, tested, weatherproof panel, ready to sit in sunlight and generate electricity for decades. That's how ordinary sand becomes a solar panel. Purified into silicon, sliced into wafers, transformed into working cells, and sealed into a device that quietly powers homes for a quarter century. Precision most of us will never see, until now.